1, constant velocity. Introduction. The three main purposes of this experiment were to observe the motion of an object with a constant velocity, calculate the expected final position using computer tracking software and the measured final position, and to compare the differences between these two calculated positions and explain why using Newton's laws and general physics. The main result was that we found that the computer model's expected final position was further along than what we measured from the video, as in we expected the system to travel further than it did. The physics ideas and equations we used were, as the basis, Newton's second law. This relates the net force, which is the net interaction between the system and its surroundings, to the system's motion. We have F net is equal to delta P over delta T, and F is equal to ma. Through this, we can derive the velocity update formula of Vf is equal to Vi plus F over m times delta T, and here I derived it on the right. We also have the displacement update formula, which calculates V average as delta R over delta T, and then RF is equal to RI plus V average times delta T. Here are the assumptions. We're going to say we have constant velocity, which is when Vf is equal to Vi. We also are going to use the velocity update formula. And then in order for these two equations to be consistent, we know that the net force, mass, and or time must be zero. Actually, mass can't be zero. And because neither mass nor delta time are zero, we know that the net force must be zero for constant velocity, or else we have Vi plus some non-zero number equaling Vf, which would be inconsistent with constant velocity. So that means we can assume that the net force on the system is going to be zero. So that means net force of gravity and friction and other things will all be zero. And it also relates to Newton's second law because F is equal to ma should be zero. Here we have the tracker of the experiment. Here's the video. I'm going to cut it short. Here we have the tracker stats. I couldn't include all the points, but this is like the first half almost. And here's the position versus time of the tracker, which shows a positive, somewhat linear relationship. And I'll say why it's somewhat instead of just linear later. And here's the coding. So I modified the mass to be 0.06, which was the weight of the expo marker, which is our system and our surroundings was the table. Here we have the balled up position, which is this point right here. We have the velocity, which I used calculating V average as delta R over delta T, which is like these 2 points subtracted over these 2 points subtracted, and delta T is 0.033 seconds because that was the difference of each frame. Here we have T is less than 2.567 because that was the last second of my video. F net, as stated earlier, must be the zero vector. Velocity is defined by this velocity update formula that I talked about earlier, and same thing with position. And we know that F net over m times delta T equals zero, so that gets us Vf is equal to Vi, which would be our constant velocity. And then our V average is the same throughout because of constant velocity, so it's just 0.494. Here we have the code output of a constant velocity of 0.494 and also a direct positive linear relationship. And this is just like a model, visual model. The differences is that you can see that the position expected was substantially larger than the position actual, which was from the actual end of result. And the reason for that is one of our errors is that we have an incorrect assumption of zero net force. The code correctly models zero net force for velocity update, but in real life there's going to be some sort of friction or some other net force or some other force that applies a non-zero net force, which is going to lead to a graph that kind of tapers off instead of being constant and linear. And another source of error is that the tracker frames had to be manually inputted, which would lead to some sort of human error of incorrectly calculating the position of the system at every given frame. And here are the what ifs and what are, or what does it mean? The what if is, in the video I had the axis point its positive x direction to the, or axis to the right. If I were to flip the axes, the overall idea would remain the same, but there's going to be a linear positive relationship between position and time. But what would change is the direction of the relationship. So instead of a positive linear relationship, it should just be a negatively linear relationship. So position decreases as time increases. And what does this mean? It means we can't determine how many / what pushes and pulls there are for the system, as in we don't know we can't calculate net force to be exactly zero. Obviously, we know that there wasn't because our results showed that there was a difference between the model and actual graphs, and we modeled as zero net force. But also there's just too many factors, such as like the table's friction, the marker's friction, gravity, air temperature, and other things like that which would affect the results of net force that we just simply can't calculate. And that's it.